All right, so this is the problem that we're going to be approximating, but before we do any of this, what I first want to make sure is that we get comfortable again with what does it mean when we approximate a function. And so I'm going to take you back to your MPR 213 course and also just bounce off a little bit of two approaches that we could go to try and approximate. Okay, depending on how we think about the problem and depending on what we have available about the problem. So to make things simple and concrete, here I have a cantilever beam. So it's clamped here. You can see the slope is 0 there. It doesn't move here, and the y doesn't displace in y. So there's a clamped grounding condition. Just by looking at this, I can tell you that. And then essentially we have some loading that's applied. And then here's the undeformed structure. And if I add the displacement field to this undeformed structure, I get the deformed structure. Okay. So this is what we have. Okay. So in this case, the displacement field looks like it's the same as the deformed structure just because our undeformed structure was just zeros. So if I wanted to get the deformed structure's geometry, I would just say it's going to be 0 plus Vx. Okay. Okay, so the bottom line is we want to try and approximate this. And what I'm going to tell you is we're going to approximate it with a specific form. I'm going to assume the form with which I want to approximate this. And if I eyeball that thing like this, I can say, you know, it looks to me like it's a quadratic. And the beauty is, let's see what we get out. Well, we know it's not a quadratic. We know it's x squared and x squared here. So it's fourth order terms that are in this displacement field. And it must be something that's fourth order because we're differentiating it first time to get the slope. We're differentiating it twice. Then it's something proportional to the moments. A third time proportional to the shear force. A fourth time proportional to the distributed load. And so what I can see is here, if I take 4 times the derivative of this thing, that Q is going to be popping out as something that is related to the distributed load that's applied. So I can see that this is a distributed load from the solution here. Okay. But the bottom line is I'm going to assume only a quadratic function. And I'm going to say let's just approximate it by ax squared plus bx plus c. Okay, so that is the approximation that I want to try and do. So there's 2 ways of thinking about how to go about solving this. And the first one is to say, imagine I take a couple of dots along this structure. So I put a couple of dots on the structure points. And I look at the displacements only of those dots. So I've got a couple of discrete points where I know what the displacement was. And let's say I've got n of those points that I put in the structure. N of these x's that I say, now I know what, and I measure then what is the displacements there. Then I can say, fantastic. This allows me to say, plug in those value for x1, yeah, plug in the value for x1, and I know what's the displacement. This then must be equal to v of x1. Plug in the next value for x2, the second coordinate. So this x1, xn it's not a dimensionality thing of x. They're all 1D. These x's, they are just a number. So if I put in x2, it's then ax squared, ax2 x squared plus bx2 plus c. Okay, and I want that to be equal to v at x2 that I've now measured and all these things. And I can then set out a system of equations like that. So I can put it, I can substitute n times the x values into this, and I know the n times those values in terms of the displacements. So if I were to plug in those x values in here, I would get the displacement if I had made no mistake in my measurements. Okay, but the bottom line is that gives me then 6 equations: 1, 2, 3, 4, 5, 6. If I have only n as equal to 6. So this is what I've written out here. And those 6 equations I can write like this. These are just the coefficients that will multiply with it. So this a will multiply with the x squareds, first column. The b's will multiply with the x's, the linear terms. And the c just multiplies by 1 because it's just the c constant, just to make sure that we can recover the c's as part of the equation. So this is ax1 squared plus bx1 plus c equals to v of x1, and it's just that 6 times. Now we need to be able to solve this, and so this is what's called an overdetermined system of equations. Okay, and I'll show you how we can solve this. But this is solvable, but not exactly, because what it is saying to satisfy 6 equations with only 3 variables as an unknown. So what we can say is we can't solve this exactly unless these equations are just a lot of time repeated. But if they all contribute unique information, this is impossible to approximate. I can't get an exact solution to this. The best I can do with this is I can give you an approximation off the bat. Okay, just visually you can see that because I've got 6 equations, only 3 unknowns. The other aspect that we can try and follow, and this is the approach that we'll follow in this course, is the continuum integral approach. And it's just a fancy way of saying essentially we're going to solve the same problem just in a different way. So imagine now we knew v of x at every point, like we have this function here. So what I can then do is to say, okay, I have this function, okay, but I want to approximate this function. Because maybe this function is just a black box thing. It's maybe something I can evaluate. I can put in stuff there and out pops answers. I might not have it in explicit form. Doesn't matter. But the point is if I have a sort of a field description of what I'm trying to approximate, then essentially I can go for an approximation that I say what's the best quadratic that will describe this fourth order function. Okay, so that's essentially what we can say. The way we can follow that approach then is essentially by saying subtract these two, the one that we want to try and approximate and our approximation, get a residual, that's what we just call residual, just square it, okay, dot product the thing with itself, so square this residual. That's just making sure that we have something now that is essentially an error, so it's always a positive quantity, doesn't matter if A, B, and C is good or bad. And then I can say we can integrate the error over the domain of x, okay, from 0 to 1.5. And before I stop this video, because I'm going to stop the video here and then I'll make a follow-up video where we'll start talking about the solution of this. But before I do that, what happens if I integrate over x? So what would happen with this expression and this expression that are sort of now subtracted and then squared? So I don't care about the details of the expression. I just want to ask you, when I integrate over x, what is this a function of? Because if I integrate v of x over x as a definite integral, what happened to the x's? Well, I substitute values for them, this definite integral. So they become constants. Yeah, they become values, numbers. So v of x integrated from 0 to 1.5 is not v of x anymore. It's just now some number, okay? Some area under that sort of displacement. That is essentially what it is. If I integrate g, which is also a function of x, and then a, b, and c, if I integrate this, so let's say from 0 to 1.5, then all the x's will become numbers, yeah? And what I'm left with are just the a, b's, and c's. And this is why, once I've integrated from 0 to 1.5, this expression, that is a function of x and then a, b, and c, and the v of x is just a function of x, what I'm left with is an error term, which is only a function of a, b, and c. And that is important. So when we integrate over a variable, that variable essentially becomes a number. That is important to understand. But also, don't forget, the units would change, because if we spatial integral, then we multiply by meters. So that is what happens. But that x function will just be out of the way. And so what I have here is, I just want to compare the two. On the left-hand side, I started off with a g of x, a, b, c, yeah? But if I look at what's going on here, for all of those x's, I've substituted values. Yeah, so these are now at points that I've chosen. These are now points that I've, so these are just numbers. These are just numbers, and it's only a function of a, b, and c. By doing the same on the integral approach and integrating over x, I end up with something that's also just a function of a, b, and c. So these two things are equivalent in terms of what they are a function of, but there are two different approaches to solve the problem. So this discrete approach is really what I'll say is the machine learning data science approach. All of those GAN faces that you've seen, fake people and all that type of stuff, follows this approach. This is a multi-trillion-dollar industry in the world today. Is how to approximate functions using this kind of discrete approach. It's a huge, huge, huge industry. This is what's made lots of companies who in what they are. Facebook and Google and all these places have really relied on solving this kind of problem. Just for problems that people care about, then there's lots of money involved. So this is the discrete approach. And this continuum approach is sort of an approach that is really starting to take off in the machine learning world, in deep learning world. But it's a lesser known approach. And it requires a little bit of more statistics typically. But this is the foundation of, I would say, modern machine learning and deep learning when it comes to sort of AI machine learning. But in this course, it's going to be our sort of old approach to approximate functions from a physics point of view. Okay, so hopefully this gives you a good idea of what we're going to do. And then in the next video, we're going to start tackling about how do we solve this discrete problem and how do we solve this problem. And I'll show you two very easy ways, and then we move forward from there. Thank you.